With that said, let's step into some examples here. So example applications on how to use a step-by-step process. Let's study the problem of an elliptical cross-section. Everybody has looked at the circular cross-section. You saw that in your more basic strength of materials, but they didn't give you the problem of elliptical cross-section. What happens when I try to torque a body of material that has a cross-section that's ellipse, right? That's a very interesting problem. Imagine a cylinder that's has a cross-section that's like an ellipse. If you, the question they're asking here is, what is the shear stress? Where is the max shear stress occurring? What is the torsional constant? And does the plane come out of plane? If it comes out of plane, how much? By how much? Very good questions here that we can study using the concepts that we discussed. Now, let me remind you, the ellipse can be described by this formula. X squared divided by S squared plus A squared, which is the distance between the point O and the outer fibers of the ellipse, plus Y squared divided by B squared, where B is the distance to the minor axis, and this is equal to 1. That formula everybody should know from pure geometry. Let me remind you the steps. The first step is to choose a function that gives me a Prandtl stress function of 0 at the boundary, because phi is 0 at the boundary due to Cauchy's relationship, as I'm not applying any traction loads on the surface. That's why that is. Number 2, I'll plug in the Prandtl stress function into this. It's not a biharmonic equation, so I apologize for that, but you'll plug it into this equation here. And once you do that, you'll be able to solve for phi in terms of alpha, either by solving the differential equation or by some other technique. You can then plug in phi into this equation here, where the torque equals the integral of 2 phi dA. And when you do that, you'll find a relationship between torque and alpha, the angle of twist. We can then calculate the torsional constant coefficient, or the polar moment of inertia J, for this cross-section. And then you're going to be able to solve for shear stresses and ignore this on the right-hand side. And then you'll determine the warping function by integrating these equations. So let's step into the actual solution process. So I'll choose a function phi that satisfies this boundary condition. Well, what I did, I put a constant in front, m. I multiplied it by this equation here. And when you do that, you can see quickly that this phi is 0, doesn't matter what values of x and y you select. Why? Because what I did a little trick. I took this equation minus 1, and that describes the ellipse in the first place. So if I put 1 to the other side, that's 0. That's my trick. So I just chose that and put m in front and left it as a constant. Great. Phi is always 0 at the boundary. I don't care what you do. That's going to work every time. Now I'll plug in, this satisfies phi equals 0. Done. Now plug this equation. I'll plug this equation into this differential equation, partial differential equation. When you do that, you will see that all this stuff simplifies very easily. So like, for example, the first partial of this gives you 2x. The second partial gives you 2 over a squared. And when you do that, you also get 2 over b squared, and that will be equal to the minus 2g alpha. I can actually solve for the coefficient m now very easily. And m becomes this equation right here. Very simple equation where g is a shear modulus. A and B are just the properties of that ellipse. Remember, A is a major, is basically the distance between the center of the ellipse to the major axis, and then B is the distance from the center to the outer fibers in the minor axis. Is this clear so far? How I calculate M? Guess what? Now I know what phi is. I'm done. I'm done. I know what phi is. Phi is this formula here. Do I know what phi is? Yes, I know what phi is because I know the shear modulus. I know A and B, these are geometric parameters. And the only thing now is that phi is in terms of alpha, which is great. Now I plug in phi into this integral. And when you do that, you get the moment, and I'll let you do that in Mathematica. Do that in MATLAB. Don't do that by hand, please. Okay? When you do that, you get that moment equals shear modulus times pi a cubed b cubed a squared plus b squared times alpha. Guess what? Now I know what the moment is. If I apply a torque to that elliptical cross-section, if I apply that, I can tell you how much it's going to twist. Right? Do I know the shear modulus? Do I know the geometric properties of the cross-section? I do know them. So I know this very well. I know how M is related to alpha. I can then calculate a torsional constant. And when you do that, you get J equals this. And in fact, if you look it up, you'll find that this is the polar moment of inertia for an ellipse. In fact, you can look it up. And notice here how J equals moment divided by G alpha. Good? Making sense? Yes? Making sense? If you plug in this phi that I found here, and I plugged it into this phi here, I can get the shear stress now. And the shear stress will be this equation. I also calculate the shear stress for tau yz, the other shear stress. That's the shear stresses. Now I also know the shear stresses for the problem along the whole ellipse. And in fact, the maximum value is going to happen. You can compare this to this and figure out which was the higher. One thing you can do is plot them in Mathematica or MATLAB to see which is the highest. But the highest is going to happen at x equals 0 and y equals b, it turns out. And when you look at that, you're going to get 2m divided by pi ab squared as a maximum value for shear stress. That's where the structure is going to start initiating a failure point. You can then plug in phi. I already know phi from this equation here. I found phi here. You can plug in here and then integrate it once to solve for kappa. And when you do that, you find that kappa is this equation here. So this is telling you that the deflection, that the ellipse is going to come out of the page in the z direction. It's going to warp outside the page. To remind you what warpage meant, that's warpage. So I have something coming outside of that plane. It's straight, and it came out in the z direction outside the plane. Beautiful. I know the max shear stress. I know how much it's going to twist. I know how much is going to come out of the page. I know all of that. And if you wanted to plot it, it's going to look like this, the warpage out of the plane. That's how it's going to look in real life. It looks quite complicated. You know, it's positive on this quadrant, negative here, and positive here. It's going to do some twisting going on, but that's the warpage equation for that. So for circular cross-section, can I just use everything I did for the circular cross-section? How do I do that? Thank you, man. Let's go off record here. A equals B. A equals B gives me a circle. So do I need to rederive all my equations? No. And this case should come back to what you studied back in strength of materials. Let's see if that's true. So when I go here and I look it up, you will see that this side, I will just use the same equation. But now for B, you saw for B I chose A, right? Just like what you said. For B I chose A. And now I get M as that just simple formula there. You can see everything simplifies very nicely. Moment becomes this, very simple. I chose B to be A now. Everything in terms of A. Now A cancels out very easily. In fact, you get the J equals pi A to the 4th divided by 2. Guess what? Look it up in your strength of materials. That was the polar moment of inertia for a circle. Look it up. Solid circle. Very cool. That we're able to derive this using this theory. Secondly, you can find where the max stresses happen. If you go back and you check, you'll find that max stress happens in the outside circle, outer boundaries of the circle. It's 2 times the torque applied pi A cubed. That's what you get. And the warpage, guess what? Since it's a symmetric cross-section, A minus B squared, B is A, is 0. You don't get that cross-section does not come out of the page because of that. Any questions so far on that circle one? No questions on that. Let's move to the triangle then. For the triangle one, we chose a function like this. Why? Because what we did is we chose each of these lines here. Each of these lines are so the equation of each of these lines basically are multiplied by each other. And they're multiplied by each other so that on purpose we get phi equals 0 at the boundary. So they chosen a very smart way. So phi 0 out of the boundary And then we just left a k coefficient in the front that we need to find. You see what I did there? So each of these equations here represent the equation of each of these three lines, and they're multiplied against each other in a smart way so that when I plug in x and y, doesn't matter what I plug in, I get 0 at this boundary, which is phi needs to be 0 at the boundary due to Cauchy's relationship. Step number 2, I plug it in here into this equation, and when you do that, when you work it through, very cool, you get the k will be equal to the minus g alpha divided by 6a. Now, this is an equilateral triangle, so the only thing defined here is a here and then 2a here. So that's it. And then now you can plug in phi into this equation now. And when you do that, you get the moment equals that, where IP is this equation here. So now you know the moment in terms of alpha. In other words, if I apply a moment, I know how much it will twist. Correct? Correct? If I know the geometry of the triangle, A, then I know IP. I know IP. I know the shear modulus of the material. That's something you can measure in the labs. You know alpha. You apply torque, you find the twist. If you apply the twist, you can find the moment. And then you can find the shear stresses very easily using the Prandtl stress functions. The maximum stress actually happens at a comma 0, which is over here for that problem. Did I figure out by just memorizing? No, you just plot it and you'll find that it's there. That's the max stress. The displacement contours are going to look like this. When the warpage is going to look like this, it's going to come out of the page again. The max stress is going to look like this. So if you know how much torque you're applying, you know how much A is, you know the geometry basically, then you know how much shear stress you have. That's what the formula is giving it to you. Example 4 is not a real example 4. It's not a real example 4. What this shows is there are books that provide for different geometries. It provides, like for an ellipse, it shows you what the max shear stress is, and it tells you how much it will twist. I already derived these equations for you, at least for this one. For the triangle, I also derived it for you. I just did it right now. For a square, I didn't do it because it's a lot more complicated. If you're interested, you can come to me and I'll show you how that's done. It is a very involved process. It can be done in a more advanced course. I teach how to approximate it, how to approximate a solution using something called a Ryder-Ritz method. We will not be doing it here in this lecture because of the complexities involved in that derivations. But you can find the shear stress at point A is where the max stress occurs. And then you can calculate the angle of twist, and then you can you'll be able to then find for various ratios of A over B for rectangle, you can find the twist theta, which is in terms of beta. Just check it out. It's very straightforward. Yeah, if you're gonna have an I-beam that you want to twist, then you have to use you're gonna have to use multiple pieces, multiple rectangles. He's gonna have a lot of warpage. So I don't know if that's the best application for that. But an airfoil for wings that looks like a fish, that's a real application that you will see. And I actually covered that example in a more advanced course. You could have a hollow rectangle, and the solution is given here on the right-hand side. Also, a hollow circular tube as well. The formulas are given here. And for a hexagon, which is more of I don't think I've seen that very much, but here's the formula for that. But all these equations are derived in a very similar step process. Step 1, 2, 3, 4, 5, 6, 7, 8. Very systematic, but some of them you cannot do it by hand very easily. You will have to take one or more advanced courses like they want to have for that. But just, it's more advanced, more involved.